Lesson 5, Linear Quadratic Systems. Our goal for this lesson will to solve problems that involve the intersection of a linear and a quadratic function. In other words, where does a straight line intersect with a parabola? Recall, the graph of a linear function represents a straight line. The graph of a quadratic function represents a parabola. A linear quadratic system is just simply a system involving both a linear function and a quadratic function. In grade 10, you spent a whole unit on systems of linear equations. You may recall you looked at where two straight lines could possibly intersect each other. The ideas from that unit in grade 10 will be applied to linear quadratic systems in grade 11. The locations where a linear function crosses a quadratic function represent the solutions to that particular problem. And we're going to look at the three possibilities of how a linear function can intersect with a parabola. The first case is no solution. In this case, the parabola and the straight line don't cross each other at all. This can be seen in the picture above. In the second way, we have one solution. Notice that the parabola and the straight line cross each other at one location. I'll indicate this right over here. In this case, you can think of the straight line being like a tangent line to the parabola. And finally, we could have two solutions. As you can see in the picture, the straight line crosses the parabola at two locations. Now that we have seen all the possible scenarios, here's how we can find them. When determining the solutions or the points of intersection to a linear quadratic system, we can find the solutions either graphically or algebraically. If using the method of graphing, you would graph each equation and visually determine the points of intersection. As you can imagine, this method isn't very accurate. If you were to algebraically solve the system, you would use the methods of substitution or elimination to solve the system involving the linear function and the quadratic function. In example 1, you're asked to graphically determine the points of intersection for the straight line f of x equals x plus 3 and the parabola g of x equals x plus 2 all squared plus 1. Take a moment to pause the video. Graph each of the two functions on the grid provided, try to estimate the points of intersection visually, and when you're ready, click play to resume. Let's begin. We'll start off by graphing the linear function f of x equals x plus 3. This is a straight line with a y-intercept of 3, which I'll mark on the grid here, and a slope of 1. So that means to get another few points, you have to rise by 1 and run by 1. I'll use that to plot a couple more points on the grid. Feel free to draw a straight line through those 3 points, and that's going to represent your linear function. Next, let's plot the parabola. This is in vertex form, so the vertex here would be located at -2, 1. Just to remind you, we have an h value of -2 and a k value of 1. So let's plot our vertex at -2, 1. The vertex is right here. And at this point, you can build the parabola using those 5 nice points, just like we did in Unit 2. Okay, 5 points is more than enough. Connect the points with the curve as best as you can. And from this, it appears like we have 2 points of intersection. It looks like we have one of them at -2, 1, and the second one at -1, 2. So we'll write a therefore statement. As you can see from this method, it's quick and easy, but unfortunately it's not always very accurate. In our case, we lucked out because our points of intersection were fairly clear, but sometimes you'll have to estimate them from the graph as best as you can, and that's perfectly reasonable depending on what you're asked to do. Let's move on to example 2. In this example, we're asked to determine the points of intersection. We'll do so algebraically now. Unless if you're given a grid, all solutions should be algebraic. So I'm going to model how we do this first one. We're given the linear function f of x equals 2x plus 4, and the quadratic function g of x equals negative x squared plus 6x. As a good first step, we'll go back to writing these equations just like we did in grade 10 using y instead of f of x. Go ahead and number your equations. And notice now that you have a system of two equations with two unknowns. So you're welcome to use substitution or elimination. It's completely up to you. Both methods are acceptable. I'm going to use substitution in this example. So we're going to substitute equation 1 into equation 2. It's always a good idea to communicate your mathematical steps. Both of them are already isolated for y, so we just simply make them equal to each other. And now that we've set up this equation, we solve for x. Anytime you solve for x, it's always a good idea to bring everything to one side. I'm going to bring all terms to the left-hand side. Okay, and I already started grouping together like terms. So let's simplify this to get x squared minus 4x plus 4, and all of that is equal to 0. After simplifying, we've created a new quadratic equation. This quadratic equation represents solutions to the linear quadratic system that we were asked to solve in the question. At this point, you can use any method that you'd like to solve the quadratic equation. Just to remind you, you can solve by factoring, you can solve using the quadratic formula. It's totally up to you. I'm going to go ahead and solve by factoring. So we have a simple trinomial, meaning we want two numbers that multiply to positive 4 and add up to negative 4. Two such numbers are negative 2 and negative 2. So now that we factored it, we just simply look at where each of the two factors is equal to 0. And I hope you can see that we're going to get a repeated root. Here we get that x equals 2, and here we get the exact same root, x equals 2. Now notice we just found the x-coordinate of the point of intersection. To find the y-coordinate, you need to substitute x equals 2 into one of your two equations. You're welcome to substitute it into either equation 1 or equation 2. I'd always recommend substituting it into the easier equation. So in my case, I'm going to substitute it into equation 1 because that's definitely the easier one to work with. Here we go. So y equals 2 multiplied by 2 plus 4. Simplifying this, you're going to get a y value of 8. And therefore, that tells us that the point of intersection of this linear quadratic system is the coordinate 2, 8. Example 3 is a little different. Let's take a look. You're asked, without solving, determine the number of the points of intersection between the parabola f of x shown over here and the linear function g of x shown over here. So let's take a moment to think about what we're being asked to do. We're not asked what the points of intersection are, we're asked about the number of them. Remember, anytime you're asked about the number of solutions or the number of points of intersection or the number of roots, you should always be thinking about the discriminant. But be very careful here. It's not enough to just take the discriminant of the quadratic function f of x. You have to first create the linear quadratic system and then take the discriminant of the new quadratic equation. Let me show you what we do. I'll start off by rewriting both the quadratic function and the linear function below. Rather than function notation, I'll go back to using y, just because, as I mentioned before, it's much easier later on to use substitution or elimination. I'll also number the two equations. And now we have to set up a linear quadratic system. To do this, I'm going to once again use substitution. So make the two equations equal to each other. So make the two equations equal to each other. And I'll bring everything to the left-hand side, very similar to what we did in the previous example. I'll collect like terms in the meantime as well, just makes it easier later on for simplifying. We get the following for our new quadratic equation. And there you go, everyone. This is the quadratic equation that represents the solutions to the linear quadratic system. This is the quadratic equation that you should be taking the discriminant of. That's very important. So let's take the discriminant up here to the right. Recall your discriminant is equal to b squared minus 4ac. Here we have an a value of -3, a b value of -3, and a c value of 17. Let's substitute them into the equation for the discriminant. So we're going to get 9. Take away 4 times the product of -3 and 17. That's equivalent to -51. All right, and now 9 take away 4 times -51. Well, 4 times -51 is -204. And now that's 9 take away -204. That turns into 9 plus 204. Which simplifies to a final answer of positive 213. We don't really care what the number is, we just care that it's positive. So therefore, that means that there's going to be 2 points of intersection. Moving on to example 4. This would be an example of a thinking question. We're asked to determine the values of k for which the linear function f of x never intersects the quadratic function g of x. In other words, we don't want any solutions at all. So take a moment to think about what has to be true for there to be no solutions. A useful strategy is once again to use the discriminant, because recall, when the discriminant is negative, there are no solutions to that particular quadratic equation. So very similar to before, let's begin by setting up our linear quadratic system. You'll see that all of these problems are very repetitive in the process used. Number your equations. And we're going to set up a linear quadratic system again. I personally like using substitution. You're welcome to try using elimination if you'd like. So we're going to make the two equations equal to each other. And similar to before, we'll bring everything to the left-hand side. I'll start collecting my like terms just to make simplifying a little easier for me later on. And the following represents now our quadratic equation of the linear quadratic system. Here we have an a value of -1, a b value of -5, and a c value of 7 minus k, because those are the two terms left over without any x's. As I mentioned before, we don't want any solutions to this system, so our condition is that the discriminant is negative or less than 0. So let me start out by writing the discriminant. We want b squared minus 4ac to be negative. Let's substitute a, b, and c. Okay, and all of this has to be less than 0. I'll begin by simplifying. So negative 5 squared is positive 25. And now we're subtracting the product of 4 times negative 1 times 7 minus k. Let's begin by distributing the negative 1 in the bracket. Negative 7 plus k. And as we continue to simplify, I'll distribute the negative 4. So we have 25 plus 28, take away 4k, and all of that has to be less than 0. Let's collect our like terms. So 25 and 28 add up to positive 53, minus 4k has to be less than 0. And now we can go ahead and solve for k. So I'm going to bring the negative 4k to the right-hand side of the inequality. 53 has to be less than positive 4k. Dividing both sides of the inequality by 4 gives us the following. We've shown that 53 over 4 has to be less than k, and that's going to be the condition that ensures the linear function never intersects the quadratic function. I'll finish this off by writing out a therefore statement. So therefore, we have no solutions when k is greater than 53 over 4. You're allowed to change the order that you write the inequality. Just be consistent with the greater than or less than sign. Moving on. In example 5, we're asked to determine the points of intersection between the line y equals x plus 6, and to make it a little more interesting, the circle x squared plus y squared equals 36. So we're asking where a line can cross a circle. The strategy we're going to use is very similar to what we've used before for determining where a line crosses a parabola. Let's think about all the different ways that a line could cross a circle. So in one scenario, you might have a circle and a line that don't cross at all. Very similar to when a line doesn't intersect the parabola. In another situation, you might have a line cross a circle exactly one time, just like I'm sketching over here. In that case, the line is tangent to the circle. And finally, you could have a scenario where a line crosses a circle twice, just like this. Those are the only 3 scenarios in which a line could cross a circle. To figure out what the points of intersection are, we're going to use substitution just like we did in the previous examples. So I'm going to substitute the line y equals x plus 6 into the equation for the circle x squared plus y squared equals 36. Here we go. So for the circle, we have x squared plus y squared equals 36. For y, I'm going to substitute the equation of the line x plus 6. And just to make it clear what I'm doing, I'm substituting this expression for y. You'll see now that we have one equation where the only variable is x, so we're going to collect like terms and solve for x very similar to what we did in the previous examples. So we've got x squared plus x plus 6 all squared. You have to FOIL that out. That's going to give you x squared plus 12x plus 36. And all of that is equal to 36. Let's now collect like terms by dropping the brackets. So we've got x squared plus 12x plus 36. And once again, all of that equals 36. Now you can start simplifying. You can add up your x squareds. And notice something nice happens. If you collect like terms with the two 36s, they're just going to cancel out because when you bring the 36 on the right to the left-hand side, it's going to become negative. So simplifying, we get 2x squared plus 12x, and all of that equals 0 now. We've ended up with a new quadratic equation, and now we solve. I'm going to solve by factoring. So let's pull out a greatest common factor of 2x, leaving us with x plus 6. And now we solve where each of the two factors is equal to 0. In the first case, we get a solution of x equals 0 because 2 times 0 is 0. And in the second case, we get x equals negative 6 because negative 6 plus 6 adds up to 0. Please note those are just the x-coordinates of the points of intersection. To find the y-coordinates, you have to substitute them into either of the two equations. I think it's easier to work with the first equation, the equation of the line. I'll just number them up here. So I'm going to substitute x equals 0 into the first equation. After doing that, we get a y value of 6. And similarly, I'm going to substitute x equals negative 6 into the first equation. Doing that, we get negative 6 plus 6, which adds up to 0. And now we can write a therefore statement. So therefore, we have 2 points of intersection. So the POIs are 0, 6 and negative 6, 0. Moving on to our last example, we have an application question here from physics. Let's read through the question. We're told that a speeding car travels past a stationary police officer at a speed of 30 meters per second. As a result, the police officer begins to accelerate until they catch up to the car. We're told that the car is caught after traveling 200 meters past the police officer, and we're given the two equations of motion representing the distance traveled by both the speeding car and the police officer. These are shown below. So notice that the equation representing the distance traveled by the speeding car is just a linear equation, and the equation representing the distance traveled by the accelerating police officer is something that resembles a quadratic equation. Here, d of t represents the distance traveled by each car, and t is the time that they've been in motion. We're going to determine the time at which the police officer catches up with the speeding car. I hope you see that this is just an application of a linear quadratic system. In other words, where does the equation representing the straight line of the speeding car intersect with the equation of the parabola representing the distance traveled by the police officer? Here we go. To make life easy, I'm going to write out the two equations, not using function notation. I'll stick with d and t rather than x and y just to be consistent with the variables presented in the question. After numbering the two equations, you'll see that we have a system of two equations with two unknowns. I'm going to go ahead and use substitution. So let's substitute equation 1 into equation 2. That gives us 30t plus 200, which has to equal 2t squared. I'll bring the 2t squared to the left-hand side. And all of that has to equal 0. Here's our new quadratic equation, and now we solve for t. I'm always a fan of using factoring rather than the quadratic formula, so I'm going to begin by factoring out a greatest common factor of negative 2. After doing that, I get the following simplified expression in the brackets. It looks like that expression can be factored. It's a simple trinomial. So we need two numbers that multiply to -100 and add up to -15. It looks like -20 and +5 are going to be our two numbers. Now that we've fully factored, we arrive at two solutions. So the first one is going to be +20, and the second one is going to be -5. But let's interpret our solutions. Notice that one of our times is negative. That means that the police officer catches up with the speeding car 5 seconds into the past. I hope you know that we can't travel backwards in time, so this solution is going to be inadmissible. So we neglect t equals -5. Make a little comment. You can say negative time is not possible. And now we'll write a concluding statement. So therefore, the police officer catches up to the car after 20 seconds. And there you go, everyone. That's lesson 5 finished. Here's your recommended homework from the textbook. Try out as much of it as you can, and I'll see you in the next lesson. Take care.